Here is a nice little puzzle that may reframe your view of probability. This is the setup. Pick a random integer from 1 to 1000, and pick a random integer from 1 to that number. Now pick a random integer from 1 to that number. Now pick a random integer from 1 to that number. And do this until we pick 1. Assuming this process is truly random, what is the expected value of the number of times this random choice happens before we hit 1? This puzzle is very hard, so take your time, and I'll give you a few hints before the whole solution. Okay, first hint. Try, instead of picking a number from 1 to 1000, pick a number from 1 to 2. This is just 1 or 2. How many times will it take you to get from 2 to 1 on average? Second hint. Once you have the expected value for number 2, try doing number 3. And try doing from 1 to 4, 1 to 5 even. Last hint. Find the difference between P of A plus 1 and P of A, where P of A is the expected value of the number of choices before getting to 1 starting from A. Okay, that's all of your hints. Here's a solution. Let's use the first hint by finding the average number of times it takes to pick 1 starting from 2. This is essentially the amount of times it takes for a coin to land on heads, if you think about it. In order to calculate expected value, just multiply the probability of an event happening by its weight, then just add all of these weighted sums together. There's a 1/2 chance of choosing 1 the first try. There's a 1 in 4 chance of choosing 1 the second try, because you need to deliberately miss the first one and then hit the second one. There's a 1 in 8 chance for the third time, and at this point you get the feel for it. It's 1 over 2 to the n for the nth try. Now we have to sum the infinite series n over 2 to the n for positive integers n, so you have to multiply by n and not just take the probability. This seems difficult because it kind of looks like a geometric series, which we know how to sum, but the numerators of the terms follow an arithmetic sequence. This type of sequence is technically called an arithmetico-geometric sequence, because each term is a product of a term in a geometric sequence and an arithmetic sequence. So how do we evaluate this? Here's how you do it. Set it to x, and then we can find that x over 2 is the same as x, but with each numerator shifted over by 1. Now we can take the difference between x and x over 2, and each term of x over 2 corresponds with the term of x, but the numerator is exactly 1 less. So the difference is the infinite sum 1 over 2 to the n for positive integers n, and we know how to sum that using this formula. So x, the expected value of the number of times, is just 2, which makes sense as the probability is 1 in 2 of picking 1. What is P of 3? Let's break the process into 2 steps. The pick something that isn't the highest number step, and the everything else step. The first step is interesting because it could be infinitely long in theory, but it will always end up as an arithmetico-geometric sequence. The probability of getting off of 3 first try is 2 out of 3. The probability of getting off of it on the second try exactly is 2 in 9. The probability of doing it on the third try is 2 in 27, and the nth try is 2 over 3 to the n. The expected value of this will be the sum 2n over 3 to the n for all positive integers n, and we can call this x again. Now x over 3 is the sum 2n over 3 to the n plus 1 for positive integers n, then x minus x over 3 is the sum of all 2 over 3 to the n for positive integers n, so we can use the geometric series formula again, and we solve that x equals 3 halves. So it takes 3 halves of a move to get off of 3, which sounds about right since it's a bit more than 1. Now there's an equal probability of choosing 1 or 2 after these 3 out of 2 moves. So the expected value of the amount of choices during phase 2 is the average of P of 2 and P of 1, which are 2 and 0 respectively. And P of 1 is 0 because you're already at 1 if you start on 1. Thus, P of 3 is 2.5 moves. It seems that we can generalize this, so we can take P of A for some A. The probability of getting off of A in 1 move is A minus 1 over A. The probability of getting off in 2 moves is A minus 1 over A squared. 3 moves is A minus 1 over A to the third. And then x over A is the same thing, but with a period shifted over 1, and we can subtract these two now. So this simplifies very conveniently using that formula to x times A minus 1 over A equals 1, so x is just A over A minus 1. The amount of moves in phase 2 is just the average of all P of n for positive integers n less than A, which can be expressed as S sub A minus 1 over A minus 1, where S sub A denotes the sum of P of n for all positive integers less than or equal to A. And if you add A over A minus 1, P of A equals S sub A minus 1 plus A over A minus 1. And we can finally use the last hint by finding the differences between 2 consecutive terms of the sequence of P of n, which is just P of n plus 1 minus P of n. Now we know that P of n equals S sub n minus 1 plus n over n minus 1, so that means that P of n plus 1 equals S sub n plus n plus 1 over n, using the fact that S sub n is just S sub n minus 1 plus P of n, we could simplify s sub n to n times s sub n minus 1 plus 1 over n minus 1. Then p of n plus 1 minus p of n, which is the difference between two consecutive terms, is this expression. And after some messy algebra, this simplifies very nicely to 1 over n. So the difference between two consecutive terms after the first two is 1 over n, which means that p of a is just a sum of 1 and 1 over n for all positive integers n up to a minus 1. Of course, the extra 1 is from the fact that p of 2 is 2, and we'll add 1 to all the following terms. The series is really similar to another series, which is called a harmonic series, and that diverges to infinity, and we know with calculus that this series increases with a natural logarithm of a, plus a special constant called the Euler-Mascheroni constant that equals about 0.577. This is more accurate the higher a gets. Now, plugging in the natural log of 1000 minus 1 plus 0.577 plus 1 gives about 8.48 times to repeat this. Thank you to @CamBrown5633 for pointing out the adding 1 error in my original video. After running their JavaScript program and my own Python program, both of which are in the description, this result was verified. And you can try this on your own with your own numbers, but its expected value will always be about natural log of a minus 1 plus 1.577. By the way, that constant I mentioned earlier, the Euler-Mascheroni constant, appears in a lot of mathematics, but it's considered to be very mysterious, unlike the more well-known constant e in pi. It's very close to 1 over square root 3, but that's probably just a coincidence. Oddly, no one even knows if the constant's rational, which is weird. Many of its properties are open problems in math today, and it even appears in some formulations of the Riemann hypothesis. That's all for today.